Okay, I think this should be working now. All right, sorry for the little delay. So everything seems to be working now, so we can start. And welcome everybody to this September nanotalk. And today our topic is about physics. And before we start, I just want to introduce you quickly to Reach. So who we are. So here is a quick, just a few slides to show you what Reach is doing. Basically, so Reach is a think tank that is based in Switzerland, and we are doing activities to basically bring closer society and researchers doing science and politics. And our topics that we work on range from a lot of very socially relevant questions, from digital change to culture, human health, and resources for tomorrow, climate change, these kind of subjects, for example. And I just also want to point out to you that besides the nanotalks, which you're seeing now, we have a lot of other formats to communicate and help scientists communicate with society and politics. And you can see some of the example here, and you can also go and check them out on our website to get more detail, or get in touch with us if you want either more information or if you want to be active in Reach, become a member, and you can meet a lot of us in Zurich, Bern, Basel, and also now more and more in Romandie. So our nanotalk today is about physics, and you will learn, or we will learn, how research into material physics can help us figure out things both about improve everyday electronics, but also things about the universe. And for this, we have two speakers today. The first one is Luca Rueg, is a master's student at the Department of Physics at the ETH Zurich. And our second speaker is Marek Mates, who's a postdoc at the Department of Material at the ETH. After each talk, there will be about 10 minutes for asking questions, and you can ask your questions on Slido. So you go to the website of Slido and enter this code, and then you can type your questions there. Okay, so now I just want to give the mic to Luca, and you can tell us about physics.
Yes, I will happily do so. Thank you, Noemi, for the nice introduction. So now I guess you see my screen. And yeah, again, hi everyone, and a very warm welcome to my talk about topological insulators, or how donuts could improve our everyday electronics. In this talk tonight, I will tell you what the topological insulators means, what the insulators in topological insulators means, and I will also explain you what important role donuts can play in improving our everyday electronics. But as you might already imagine, it's a little more complicated than just taking a donut and literally gluing it on a circuit board, as I have done from my title image. But yeah, I needed to have something catchy, and now the essence about how donuts could improve electronics will come during my talk. So the first thing that you of course should ask yourself is, why do I even want to improve our everyday electronics? Because our electronics admittedly are very, very good. Here in the left picture, you see a couple of parts that you can use to build electronic circuits. And with these parts, you can basically build any circuit imaginable. The fact that you are now watching this nanotalk via your computer that gets the data from a server farm, that gets data from my computer, just shows you how incredibly good our electronics today are. But they also come with some disadvantages. Namely, also your computer or your smartphone that you are now watching this talk on is at this very moment most probably cooling itself. You might even hear the cooling system at work, because wherever electricity flows, heat is produced. You see this very directly or you feel it very directly if you touch one of these old light bulbs, because these are very hot. And the thing is that a light bulb shouldn't actually be hot, because it should produce light. But the heat that is produced in this process comes as a byproduct. But this is actually, it's not something that we want, because we have to build something in addition to cool our computers. And now you might say, okay, but that's fine, I'm fine with that. It just costs some more energy, but that's okay. Now, you can also think that if you consider these huge server farms that Google and other tech companies have, and through one of these server farms, also the data that you are seeing right now of this talk goes, and these server farms, they have a lot of computers there, and these produce a lot of energy. So one of the main tasks for building such server farms is actually to find efficient ways to cool them. And of course, we are able to do this, but it's a very large energy cost that we have there. And we all know that unfortunately our Earth is anyway heating up, so we don't want any more heat produced. So the heat that comes as an unwished byproduct everywhere where electricity flows is really the big disadvantage of our today's electronics. And to improve this, we'll first have to look at how does electricity actually flow. So why is heat being produced when electricity flows? And so one question that I would just very quickly like you to think about is, what do you think is the average velocity of electricity when it comes out of the charge plug in your wall, in normal cable? Just quickly think about it. And I'm very sure that all of you are in the same range that I thought that this velocity is just a couple of years ago, but actually it's very slowly. It's about 0.1 millimeters per second. So during the whole length of this talk, the electricity that comes out of the charge plug in your wall doesn't move much farther than this. And so now you might think, okay, how does actually electricity move anything in my computer? But the important thing here is not that it moves quickly, but that it just moves. It's a little bit as in a traffic jam. You move very slowly, but still you move. Like at the beginning and at the end of the traffic jam, you feel some movement. Okay, so it's very slowly, but why is that so, and where does the heat come in there? So if you look at electricity on a microscopic level, so if you look at the tiny electrons that constitute an electric flow, you see that these are very fast, but they move in a very chaotic and uncontrolled way. So they move just like in a pinball machine. So they bounce off the walls, they bounce off each other. But still, also in a pinball machine, there is a tendency for the balls to move downwards. And this is the same tendency that you have in in a normal electric current. Okay, so this is where the heat comes from. It's just a very chaotic movement, and in this movement, in this process, heat is being generated. Okay, so but how should it then ideally flow? And to again take the analogy of cars, I tell you that ideally it should flow like on a fast lane. This means there is a very controlled straight movement. It better doesn't bounce off the borders of the lane, just goes in one straight direction. Because in this process, no heat at all would be produced. Okay, but now, is this possible? Well, I wouldn't be giving this talk tonight if it wasn't. So yes, it is possible. And it is possible in many different systems. And these systems are these so-called topological insulators. And now I will give you a practical example for one of these, namely a thin metal plate in a magnetic field. So in this thin metal plate, you have electrons that move in circles. Because whenever an electron moves in a magnetic field, it moves in circles. This is also the phenomenon that people use in the particle accelerators at CERN, because the particles move in very, very big circles, but they do so because there they have along this ring, they have very strong magnets. And on a much smaller scale, this now happens in this metal plate. Okay, so far you don't see a fast lane here, nothing special. But if you now look a little closer at the border, you will see something. Namely, now if you have these orbits at the border, the thing is that you cannot have closed circles, because the electrons here, they will start to move, they want to form a circle, but then they bounce off the wall. And then again, they bounce off the wall, and so on. And you see that this bouncing off the walls gives you a net movement of the electrons along the border of this thin metal plate. And this movement is exactly what I've told you about before in the fast lanes. Because in a fast lane, you have a very controlled, straight movement of your electrons. And this is exactly the case here. Because what I've told you is really the exact way how these electrons move. It's not the pinball machine from before, where the electrons bounce off each other and off the walls. No, here they just move in a straight way. Good. So this directly leads us to the definition of topological insulators. Because a topological insulator insulates in the interior of the sample. So as we have seen before, in the interior of our samples, the electrons are just doing these very, very small circles. There you don't conduct any electricity. But then on the boundary, at the edge, you had these fast lanes for the electrons. So there you very strongly conduct electricity. And this is the defining feature for these topological insulators. And this is also where the term insulator comes from. Because in the bulk, in the interior of these materials, they are insulated. On the boundary, they conduct. Okay, so we have one term of topological insulators. Now let us focus on the topological. So why is a topological insulator topological, or what is that even, topological? So topology is the mathematical field that studies so-called global properties of geometric objects. And this is a very formal and complicated way to just say that they study things that don't change if you slightly deform a material. And one of these things is the number of holes in a material. So for this, I first want to show you a donut that has one hole. And now I tell you something very bold, namely I tell you that this coffee mug of mine has the same number of holes as this donut, as does my espresso mug, as does even this small elephant-shaped bookshelf stand. Because also here you have a handle, and this handle is a hole. Now you might find this very, very hard to imagine. So there's also a good figure that shows you this. So here we start with a donut. Now we deform it, and it becomes a mug. And this just tells you that donut that you see here now has the same number of holes as a coffee mug. Because in this entire process that you see here now, you don't change anything. Or you change a lot, but you don't change anything dramatic about your geometric object. You just deform it a little, but you don't cut it or anything drastic like this. And this allows us to say that the donut and coffee mugs, the handle, have the same number of holes. They are topologically equivalent. Okay, so, but what is the topology of topological insulators? Now, of course, there aren't any donuts or coffee mugs in your topological insulators. But the thing is that the mathematical structure that is behind these materials and that describes these materials can be equivalent to a donut or a coffee mug. And this is very useful because now we can state that materials that are described by a mathematical structure that doesn't have holes also doesn't do anything interesting. So if the mathematical structure behind this material is equivalent to this chocolate ball, so it doesn't have any holes, it's not a topological insulator. It doesn't do anything interesting. However, if this mathematical structure is equivalent to a donut or a coffee mug, then you exactly observe this phenomenon that we have seen before. Okay, so what this also already tells you is that the phenomenon that we have just seen of the topological insulators, that they conduct electricity on the boundary but not in the interior, is a very strong property, because now we can deform the material or the mathematical structure behind it a little, from a donut to espresso mug to another coffee mug, and still you observe this exact phenomenon. And now this is something that is very special in physics, because often when you only slightly change something, then the results will also slightly change. However, here you can very much change the material, but the result will be the exact same. And for this, this is coined the topological robustness. And for this, I just want to show you this measurement, so we don't have to understand any details about this plot. All that it says that here on the lower axis, you have a parameter that you change about your material. Okay, and here on the vertical axis, you have a measure for how good the fast lanes conduct your electricity. And the important thing that you see here is that in this entire range here, you very much change the parameters of your system, but the conductivity, the important physical phenomenon, doesn't change a bit. And this can be explained by saying that around, or in this region here, your mathematical structure behind your material might be equivalent to a donut. And then here it changes to a coffee mug, but that's fine. The physical phenomenon stays exactly the same. Only when you cut it or break it or you bite off a bit of your donut, this changes. So this is exactly what is meant by topological robustness. In this entire regime here, where the number of holes behind in the mathematical structure behind your material is the same, the physical phenomenon will stay exactly the same. Okay, so this lets us conclude that topological insulators are like fast lanes for electrons. They conduct electricity much faster, much more controlled, and much more efficiently than any cable that you have going from your computer to your wall, or any cable inside your computer does. Now you might think, okay, that's a good property, but this must for sure be very hard to implement. But this is exactly not the case, because we have seen that these fast lanes are topologically protected. It doesn't matter if you deform your material from being a donut to being a coffee mug. This phenomenon of the fast lanes persists, and this gives you like a double advantage of topological insulators over nowadays electronics, because they're more efficient and they are more stable. So topological insulators are very promising for the electronics of the future in making it more stable, more controlled, and most of all, most efficiently. And we all know that it's probably a good time to think about how we can make things more efficiently. So thanks a lot for listening, and I'm very happy to take any questions that you have.
Right. Thank you, Luca, for your talk. So anybody can ask questions in Slido if you have any questions for Luca, and I will read them. So I have one now. So you explained with the edges that the net movement that we want basically is on the edges. So like practically, if we want to use this for everyday electronics, we would have to like make a cable out of edges, or how does that work? Is that possible? Or like a cable with one hole?
So that's a super good question. And so the system that I've shown you is really just one example. And the research in the field of topological insulators has been, I mean, it's not that old, it's like 20 years old, but it has already achieved a lot of things. And one of the things that it actually has achieved is that this correspondence between the interior of your material being insulating and the boundary being conducting actually goes through all dimensions. So say you have a topological insulator that is just like a one-dimensional line, then you still have the conducting points on the edge. Now, furthermore, we have seen the two-dimensional sample, and there the one-dimensional boundary is conducting. And the same thing happens also for any 3D material where the two-dimensional surface is conducting. And the story doesn't end here, but there are more complicated ways to engineer these materials and systems, where you can also have, say, you have a three-dimensional material that has a hinge. So actually say this is our material. Then there are also materials that actually only conduct along this hinge here. They only conduct along one line. So this then becomes very similar to just a cable. I mean, of course, it doesn't look like a cable, but you can make this box very, very thin. So it's actually not any more thicker than a normal cable, but still on this hinge here, it conducts. So you effectively have the same effect as in a cable, because only that your cable then isn't a tube, but it's just a very small and thin and long box. So it's true that in the sample that I've shown you wouldn't be very practical to conduct electricity in your computer, but you can cleverly engineer these systems, and then you can make something that is just as good as a normal cable. Yeah, but it's a very good question, and I mean that was also one of the big steps that this subject had to overcome, because it's indeed not very practical if I always have to use a sheet of paper to conduct electricity. Yeah.
Thank you. We have 1 or 2 more minutes. Somebody's asking then, is this concept of topological materials already used in some systems, some electronics that already exist?
Not yet.
Not yet.
Because no, as I've told you, the field is 20 years old, and the discovery that I've just told you about with the connectivity on these hinges, that was made 3 years ago.
Okay.
So it's really a very young and dynamic field. But I for my part, I'm very optimistic, because there have been other fields that haven't produced, anything meaningful in many years. But this field really is there since 20 years and has already now taken a lot of hurdles. And of this concept of the hinges that conduct them, I think we are very close before having the first materials that you can actually use in electronics to conduct electricity.
Okay, great. So then we'll stay tuned and ask you again in a few years then if it worked or not.
Yeah, so.
Yeah. So thank you, Luca, for your talk. It was very interesting.
Thank you.
Now I will give the stage to Marek Matas, who, as I say, he's a postdoc at the Department of Materials at ETH Zurich, and is going to tell us about how we hunt for dark matter with Earth-based detectors. So we're going to learn something about the universe now. Marek, it's to you.
Hello, everybody, and welcome to my presentation. And as was mentioned before, I would like to tell you something about dark matter and about how we can discover it in Earth-based detectors. During the course of this talk, I would like to convey to you a few messages. One of them would be, what is dark matter? So for a lot of people, dark matter is a sort of this vague topic, not a very clear idea of what that is and how we know that it exists and what are the facts that we base our hunt on. And I would like to persuade you that dark matter is actually something that exists, something that is very physical, and something that we are certain of that it has a huge impact on the cosmos and the universe around us. So the way I would convey to you the message of what dark matter is that I would guide you through the discoveries that have made mankind realize that dark matter is a thing. So one of the first discoveries one of the biggest discoveries that persuaded mankind of the existence of dark matter are the so-called galactic rotation curves. It's a very fancy term, and I'm going to explain to you what it means. So if you let me guide you through a thought experiment, imagine that you have a solar system, imagine a solar system with a star in its center, and then 2 planets that are orbiting it that have the same mass. Of course, in the solar system, if you want a planet to be on a stable orbit, the 2 forces that apply to it have to be in balance: the centrifugal force and the gravitational force. If you take this planet that has these forces in balance and you move it further away from the star, then of course the gravitational force will decrease. Therefore, also the centrifugal force has to decrease. And the only way to do this is that this planet will have to go slower on its orbit. So the further away you are from a star when orbiting, the slower you are going to be moving. And that holds for planets and everything else. It also holds for galaxies themselves. If you imagine a galaxy that I show you here on this picture, the further you go away from the center, then the stars, planets, black holes, and everything that's in that galaxy will be moving and rotating around the center slower and slower and slower, if this thought experiment is correct, of course. All right. So if you would plot this, make a plot of these velocities, then on the y-axis, you would have the speed of orbit. And here on the x-axis is the distance from the center of galaxy. And you would expect a curve that would be like this, that would drop off at large distances from the center. You wouldn't even feel the galaxy. You would be rotating really slowly. But then when people pointed their telescopes and confronted this idea with an actual measurement, this is not what they have found. The plot that they found when they drew it looked like this. This is the observed velocity galactic rotation curve that you observe. Now, as you can notice, the orbital speed of these objects remains the same the further you go away from the center. Now, that is something very puzzling and something very weird and odd. How can you explain this? How can this be possible? If we go back to our idea of a toy solar system, now that would translate to the fact that the outer planet moves at the same speed as the inner planet. So necessarily, the gravitational pull on this planet has to be much larger than what we thought. This cannot be due to the fact that the star is heavier, because that would also make the internal planet orbit faster. But we can explain this by a presence of a huge pile of a homogeneous gas that would be present in that solar system, that the internal planet would be embedded in. The internal planet would not feel this gas because it would be all around it. It would be submerged in it. But the outer planet would feel a lot of this gas being beneath. It would pull on it and it would make it orbit faster. Exactly the same explanation as this can be translated to galaxies. If this galaxy indeed is submerged in some invisible gas, something that we haven't seen before, then all of the celestial bodies, the stars, planets, black holes, they will all be orbiting much faster than what we anticipated. So when people started conducting these measurements, they looked at, of course, they looked at various galaxies. This is one of the examples. Here you see measurement for 5 different galaxies. Here are their density profiles. So from this, you can see that they are indeed 5 different galaxies, but they all have these flat galactic rotation curves that are essentially telling us that there is some invisible gas of particles or additional stuff in those galaxies that we don't see. It's something that is very heavy. And in fact, if you do the math behind it, you realize that there is 6 times more of this invisible stuff than there is of all the stars, black holes, planets, etc. So this was a crucial evidence for the existence and nature of some invisible stuff being out there in the galaxies. This is not the first measurement. The first observation of this was not done in galaxies, but in galactic clusters. So this that you can see on this picture is the so-called Coma Cluster. Now, every dot in this cluster is not a star, that is another galaxy. And Fritz Zwicky in the year 1933 pointed his telescope and started to estimate what would the dispersion of velocities be in this cluster. And he realized that if he uses thermodynamics, namely the virial theorem, he can actually predict the dispersion of the velocities based on the mass of that cluster. And he did that. He estimated the mass. So he counted the number of galaxies. He looked how bright they are, and then also how far away they are, and he estimated their mass. And then he plugged this into the math, and he derived how heavy, how fast would those galaxies move in that cluster? What would their dispersion be? He arrived to a number of 80 kilometers a second, but when he then pointed the telescope and measured the velocity dispersion, he came to a number of 1,000 kilometers a second. This was a striking discovery, and again, this can be explained by the presence of some invisible matter that is really heavy, some sort of unidentified species of particles that do not interact electromagnetically, but are there and are very heavy, and this would give rise to that additional speed. He then concluded that if this would be confirmed, we would get the surprising result that dark matter is present in much greater amounts than luminous matter, as we now believe today is the case. This is not, of course, the only evidence. So far, I've been talking about movement of bodies, about speed, about something moving faster than we would expect. But there are another sets of observation, and they come from gravitational lensing. Now, from the general theory of relativity, you might know that every massive object bends the space-time of the universe. What that essentially means is that every heavy object can serve as a lens for light that is passing by. Every massive object like a star, a galaxy, a cluster of galaxies even, will bend the light. So if you have a light source and you observe it on Earth, you can see this bending effect. You can see that the light has been distorted, similar as if you look through a lens in the glasses. And then if the object that is doing this lensing is heavier, the lensing is going to be much stronger. So you can use these lensing observations as sort of a scale to weigh the objects that are causing this lensing, because then you can know how heavy they are. This has been done. This is a picture by a telescope that has such lensing event. You can see a massive object in the center that is distorting a galaxy that is behind it. And from inferring those masses, we again conclude that there is 6 times of this invisible hidden matter than we would expect. Now then, so far I've been talking about gravity, something, and Newtonian dynamics, about the movement of planets and about something pulling on something else, bending light, general theory of relativity. So you might at this point tell me, well, maybe it's not that there is something heavy. Maybe you haven't done your homework good enough and you don't actually know how the theory of gravity behaves on these gigantic scales that you're talking about. Maybe gravity is different when it comes to the whole universe and not our local surroundings. Well, people thought that this might be the case. Then in the year 2006 came this observation. What you can see in this picture is a collision of 2 clusters of galaxies. So these are 2 gigantic sets of galaxies, billions and billions of them, that have collided. And this is the picture after the collision. Now the colored map shows you the distribution of the regular matter, of the gas, of the stars, of the black holes, and of the planets. And you can see that when this collision happened, they sort of lagged behind. They collided and they dragged a little bit. They slowed down. And then the green contour, that is the dark matter that has been reconstructed through gravitational lensing. So you can see that even though normal matter stopped and stayed at one place, the dark matter passed by through itself and continued flying on to the cosmos, which then means in turn that it is not the fact that we don't understand gravity. It's not the fact that we wouldn't understand Newtonian dynamics. Dark matter is something that can fly on its own. It doesn't have to be connected to any star. It doesn't care if there is a black hole or gas somewhere. It can fly on its own through the universe. And therefore, we now believe that when you ask the question again, what is dark matter? Then this direct empirical proof of the existence of dark matter, this is the name of the paper that has been published, tells you that if you add all the evidence that we have together, we have to conclude that dark matter is an unknown particle species with a mass of 6 times that of visible matter. it doesn't interact with the regular matter in any other way than gravity, so far from we know of. But we hope and we assume that it does interact very, very weakly with the regular matter around us as well, but so weakly that we haven't been able to observe it so far. Now, how can we then detect this? We would assume that there is a possibility we can detect it. How can we do this? Because obviously it seems very hard if it's something that is out there in the distant parts of the universe. Now, for this, we can use the so-called dark matter wind. If you realize that actually dark matter forms these blue clouds, well, they're not actually blue, but they're denoted here as a blue cloud of huge halo that is formed around our galaxy. And when you realize that we're sitting somewhere here on inside of the galaxy that is spinning through this dark matter halo, we are going through this dark matter fog as if when you're driving your car in the fog in the forest, then as the Earth moves and the solar system moves forward, it is flying through those dark matter particles, and those are there then raining down on Earth. So dark matter particles are actually raining down on you every day and every second that you spend here, but they are too weak and they don't produce any observable effects that we would know of. So how can we detect them? Well, since we believe the dark matter was created during the Big Bang in a thermal equilibrium with the regular matter, so when Big Bang happened, there was this enormous density of energy, this overabundance of hot gases and yeah, huge densities of energy. And then dark matter and regular matter were created at the same time. And they were linked by some channel that they could communicate together. And regular matter could go into dark matter, and dark matter could go into regular matter. And we believe that this link is still there. And we might still use this link, however rare it might be in these days of the universe that has cooled down by a lot. And therefore, this process of dark matter interacting with regular matter will be incredibly rare. We can still build a detector on Earth that would be super sensitive to dark matter hitting it. And we can try to achieve that. Now, how can you design a detector that would be sensitive to events like these? That is, of course, a large problem. And one of the main problems is that those events that you're trying to observe are incredibly rare. Since they are incredibly rare, it is hard to know whether the observation, the signal that you're seeing coming from a detector actually comes from dark matter, or if it comes from something else that is equally rare, like a radioactive element decay that you might have in your detector, or maybe a cosmic ray that went in the detector, or well, any other possible background source that you can imagine. Now, one of the ways to tackle this is using graphene as your detector material. Now, graphene is a two-dimensional material and is the single layer of graphite, of the same material that you have in your pencils. If you would cut a single atomic layer of graphene, of graphite, then this is then called graphene. Now, and then since I told you already that the Earth and the solar system is flying through this fog of dark matter particles, those are then raining down on Earth from one direction, the opposite direction of the flight of the Earth. You can then take your graphene sheet and point it towards dark matter wind. And then the electrons that are going to be supposedly kicked out by dark matter particles are going to be flying preferentially in one direction, in the direction of the flight of dark matter particles. They will be kicked out of the plane. And then you can take your graphene plane and you can twist it and turn it and rotate it around and wait for night and day and spring and summer. And you will be still observing the direction of the flight of those electrons. And if they're this whole time flying in the direction of the wind of the dark matter particles, now that is a strong hint that what you're observing are dark matter particles hitting your detector and not actually some homogeneously distributed radioactive decaying contamination in your detector, that it's not something that's flying to the earth from the sun or from some other objects that we might encounter in the sky, but that it's actually the dark matter wind. And the directionality of this detector might be one of the ways that could help us measure and detect dark matter here on Earth. Now, of course, it's very hard to build a huge graphene detector, but a prototype has been already tested, and this is going to be a multi-purpose detector. It's not only going to serve for the detection of dark matter, it's also going to serve for detecting primordial neutrinos. So neutrinos flying to us from the very Big Bang that are very weak nowadays, but we could use this graphene detector to detect them and map out the sky similarly as we have done for cosmic microwave background. So this will be a very exciting experiment that has the potential of both detecting dark matter and mapping out neutrinos flying from Big Bang that have been created in a fraction of a second right after the creation of our universe. If I come again to the question of the detector design, this is not the only answer, of course, because we are mapping out an uncharted territory where there is the number of possibilities where dark matter can be as numerous as the number of people that work in it, and we can never think of and come up with an idea what surprise can nature lay ahead of us. That is why we're not using a single approach, but we're using a variety of materials, and each and every single one of them has their advantages and disadvantages. And by using them all at once, we're hoping to map most of the uncharted territory and be capable of discovering the effects of dark matter hitting our detectors right here on Earth, and thus realizing more about its properties, its origin, and its potential influence for the universe and then us. Thank you a lot for your attention. This has been my talk. And of course, I have barely scratched the surface here. I talked about one material and briefly introduced a whole fascinating topic of cosmology and dark matter. So if you would like to know more, you can shoot me an email and I will be glad to answer any questions that you might have or join for a discussion or anything. Thank you.
All right, thank you, Mark. That was very interesting. So there are some questions in the chat that I will read. So the first one is, if dark matter is like a gas that is everywhere, does it affect models of how planets in our solar system rotate, or is that contribution negligible?
Mm-hmm. Yeah, the contribution to the planets in the solar system, unfortunately, is negligible. The density of dark matter in our local vicinity is estimated to be about half of a hydrogen atom per cubic centimeter. That's not enough to make the rotation of planets different. However, what it does in our neighborhood is that it makes stars oscillate at a different frequency. So you have your galactic disk that is playing, and then the stars, they go like boats on the sea. They go up and down as they're moving in the galaxy. I guess if you have a boat and you're going up and down on that boat, the same happens for the stars that are in this galactic disk. And the frequency of this oscillation needs to be explained by dark matter. Otherwise, you would not get the right number. And it's actually used to estimate the local density of dark matter, which is this 0.5. So not enough for the planets, but it is enough to make us with the solar system bounce up and down faster.
Okay, cool. A bit more of a open out of science questions. In a lot of sci-fi movies or books, I guess, dark matter is used as an incredibly powerful way to power ships. Would that even be feasible if dark matter doesn't really interact with matter?
Yeah, I mean, yeah, the answer there is quite what you just said, because if you want to have something as a propellant, you most likely want it to interact very strongly. So I guess antimatter would be a much better propellant because that interacts like crazy and deposits huge amounts of energy. And if you want to move fast, you need energy. Whereas dark matter doesn't deposit any energy at all. We're struggling to detect any, and we don't see so far, mankind hasn't been able to detect anything. I think it would make for a very bad propellant.
Yeah, that might be a sci-fi movie director confusion between dark and antimatter, maybe.
Yeah, it might be, might be. I
Yeah.
guess this would be the worst propellant that the mankind knows of so far.
Okay, so good sci-fi movies. So, but there's another question. Do we actually know the nature of dark matter? And also, how do we detect it once it's gone through the graphene? Like, what's the receptor part of the detector?
So, well, the nature of dark matter is we know only a few things. So most evidence points to the fact that it's some sort of unknown particle species or families of species. It can also be multiple particles that's very weakly communicate to each other, but just some of them might be connected to our particles that we have here. What we do know is that they don't even interact among each other, or if they do, very weakly. Otherwise, they would not form these balls, these halos, but they would also form disks, just like our galaxy does. So we know it's some particle species that doesn't interact with us or with anything else except for gravity. And the way we're hoping to detect it is we're hoping for an energy deposition in this detector. So in that graphene, that would translate to the fact that it would fly in, it would hit an electron, and it would kick it out of the plane of the graphene. And this electron would then be flying, and we would measure a voltage pulse on this graphene sheet that it lost an electron. And then we would wait for this electron to fly and hit another graphene sheet. And there we would get a voltage pulse of this graphene sheet getting an electron. And from these, we would be measuring those electrons being kicked out. And by mapping, of course, all sorts of things like the kinematics, how fast did it get kicked out, how often, we would get a hint of a dark matter candidate. And we would then build additional detectors that would confirm that this is indeed dark matter and not something else.
Okay. And the last question is, have you guys detected some yet? Has it worked already?
Well, so it's actually a very exciting field because every few years there is someone claiming that they have discovered dark matter. And I'm not talking about individuals, I'm talking about large collaborations of fun physicists that have really done their homework. And because it's really hard to know if what you're seeing is or is not dark matter, then I think to this day there is I wouldn't say the few number, but out of the top of my head, I know at least about 3 or 4 experiments that claim that they see dark matter. The problem is that they both claim to see dark matter in a different region of the spectrum. They all contradict each other. And then there are other experiments that are disproving them all. So far, if you ask me personally, I think we have not found it yet. But it might be the case that we're, for example, seeing it in our silicon detectors already, but we're not really sure if it's background or not. And this graphene detector would be the one to say, look, it was true. We are actually seeing dark matter already, but it's hard to be conclusive. So far, it seems we have not found it.
Okay, that's super interesting. So we'll ask you also again in a few years and wait and see what happens. Yeah, we're arriving at the end of our hour, and I really want to thank you and also Luca for giving us the talks today. It was super interesting, and I think we learned a lot. And yes, so I just also want to thank everybody who watched. And of course, if you want to rewatch this nanotalk or watch some of the previous ones, you can find them on YouTube in a short amount of time. You can also share them with your friends and colleagues if they're interested and they couldn't make it today. And I want also to ask everybody, or invite everybody to join for our next nanotalk, which will be the last Thursday of October. And we don't know the exact subject yet because it will be about the next Nobel Prizes. So when we know the Nobel Prizes, then we can tell you what the subjects exact of the nanotalk. All right. Thanks everybody again for coming today, and have a good evening. Bye-bye.
Thank you for having us.
Bye.
All right. Thanks, guys. Sorry for the technical glitch at the beginning. It's
No problem.
yeah, it was a bit tough to deal with it with one person and the baby crying in the background. But I think it will be good enough.
Yeah.
All right. Have a good evening.
Yeah, you too.
Cheers.
Bye.
Sorry.